Hello everyone, welcome to this video lecture. I am Dr. Dibya Sivananda. I am an assistant professor in the Department of Physics of Darrang College. Today in this video lecture, I will be discussing about the Maxwell's equations, which is a topic under the course Electromagnetic Theory under Jyoti University syllabus. So let's discuss about the Maxwell's equations. Today in this video lecture, I will be discussing about the differential form of the Maxwell's equations, and later on I will show that the differential form and the integral form of the Maxwell's equations are equivalent and we can obtain one from the other. So the first Maxwell's equation is the Gauss's law, which in the differential form can also be written as divergence of electric field is equals to rho by epsilon naught, where rho is the volume charge density. So if there is a electric field coming out of a surface, then the divergence of the electric field is equals to the volume charge density enclosed by the surface divided by epsilon naught. This is the first Maxwell's equation. The integral form of this Maxwell's equations you already know as integral E dot d of s is equals to q enclosed by epsilon naught, where E is the electric field coming out of a surface and q enclosed is the total charge enclosed by the surface. You already know this. So the second Maxwell's equation is the divergence of magnetic field is equals to 0. In some books, the second Maxwell's equation is also called Gauss's law of magnetism. So the second Maxwell's equation means that the net magnetic field coming out of a surface is always 0. Now the question is, why does this happen? The reason for this is that magnetic lines of force are always continuous. So the total magnetic or the net magnetic field coming out of a surface is always 0. We will discuss in detail later on why this happens. Number 3 is the Faraday's law. The Faraday's law can be written as curl of electric field is equals to minus del V del T. So this is the differential form of the Faraday's law. The integral form of the Faraday's law, you already know it as integral E dot d of L is equals to minus d phi dt. This is phi, the flux of the magnetic field. So later on we will prove that the differential form and the integral form of the Faraday's law are equivalent. We will obtain one from the other. The fourth Maxwell's equation is a corrected form of the Ampere's law, which was written by Maxwell as del cross B is equals to mu naught J plus mu naught epsilon naught del E del T. So the integral form can be written of the Ampere's law can be written as integral B dot d of L is equals to mu naught I enclosed. So Maxwell made a correction to the Ampere's law where he included this term mu naught epsilon naught del E del T into the Ampere's law, and he wrote down the differential form of the Maxwell's equation. Now, why was the correction needed? We will discuss this in the next video lecture. So this video lecture was just the introduction to the Maxwell's equations. So all of you know about the integral form of the Maxwell's equation, which you have already studied in your class 11th and 12th. In this video lecture we studied about we discussed about the differential form of the Maxwell's equations, and in the next video lectures we will discuss about each of the Maxwell's equation in detail, and we will also discuss how we can obtain the integral form from the differential form and the differential form from the integral form.